Here we discuss about a project, a lower power, reduced error, lower part or adder for multimedia applications. Here, approximate adders are widely used in multimedia processing, image filtering, machine learning accelerators, and low-power DSP systems, where small computational errors can be tolerated in exchange for better energy efficiency and lower hardware cost. These designs provide clear advantages, such as reduced silicon area, lower power consumption, and simplified logic structures. However, when approximation becomes too aggressive, it introduces large computational errors, bias in results, and noticeable degradation in output quality, especially as the operand size increases. The reduced error lower part or adder, or RELA, is one such architecture that applies 50% approximation to reduce hardware complexity. While this approach effectively minimizes hardware resources, it significantly increases mean error distance and mean square error, particularly for larger word length operations. Most existing approximate adder designs focus mainly on reducing power and area, often at the expense of accuracy, and only limited research has addressed scalability while maintaining improved precision. To overcome these limitations, this work proposes a modified RELA architecture that reduces the approximation level to 25%. The constant logic block used in the original design is removed, and controlled approximation is confined only to the least significant quarter of the operand. At the same time, carry-aware logic is preserved to maintain structured computation. This structural modification improves computational accuracy while retaining most of the hardware efficiency benefits of approximate computing. The proposed architecture is implemented for 16-bit, 24-bit, and 32-bit word lengths using structural Verilog HDL and synthesized on a Xilinx Vertex 5 FPGA. Performance is evaluated in terms of LUT usage, register count, delay, and power consumption, along with error metrics such as mean error distance and mean square error. The results demonstrate improved accuracy with moderate hardware overhead, and scalability analysis shows reduced delay variation at higher word lengths, making the proposed design well-suited for precision-aware multimedia and DSP applications. Now we can verify this paper. This paper is completely designed for lower part adder. This figure 1 is the core of this architecture. The existing RELOA architecture operates on a 50% approximation principle, where the n-bit adder is partitioned into two equal sections. The upper n divided by 2 bits, which carry higher numerical weight, are implemented using an accurate adder to maintain result significance and prevent large magnitude errors. The lower n divided by 2 bits form the approximate region, designed to reduce hardware complexity and switching activity. Within this approximate section, the least significant n divided by 4 bits are implemented using a constant logic block that forces all corresponding sum outputs to logic 1. This eliminates full adder cells in that region, significantly reducing logic gates, area, and dynamic power consumption. The remaining n divided by 4 bits of the approximate half are implemented using a controlled approximate adder. In this section, a control signal is generated based on propagate logic from selected higher-order bits along with a carry detection condition. This carry-aware control selectively injects a carry into the approximate region to limit excessive deviation from the accurate result. Although this architecture achieves notable reductions in gate count and power consumption, the constant logic assignment in the least significant portion introduces a fixed error bias. As the word length increases, this bias accumulates, leading to higher mean error distance and mean square error, thereby affecting computational accuracy for larger bit width operations. In the proposed method, the architecture is refined by reducing the approximation level to 25% and removing the constant block entirely. Instead of approximating half of the operand, only the least significant quarter is implemented using the controlled approximate logic, while the remaining 3/4 of the adder operate accurately. The same carry-aware control mechanism is retained to maintain structured approximation behavior, but eliminating the constant block removes bias error and improves error distribution. This modification increases the accurate region, slightly increasing hardware resources and delay, but significantly improves computational accuracy. As a result, the proposed architecture achieves a better balance between hardware efficiency and numerical precision, particularly for larger word length designs such as 24-bit and 32-bit implementations. Now we can verify the result and implementation. This is the Verilog HDL 16-bit code for RELOA adder. This is the simulation results for 50% of accuracy. This is the simulation results for 75% of accuracy. Here you can verify the error difference. This 25% of adder will reduce the more number of errors compared to 50% of approximation. This is the synthesize report and RTL schematic for existing work. This is the synthesize report and RTL schematic for proposed work. We also designed the work of 24-bit and 32-bit for performance evaluation. Here, this is the comparisons table for this work. And we have written an abstract document for this project. Title: Base Paper Abstract, Improvement, Objective, Existing Method, Disadvantages, Proposed Method, Advantages, Related Notes, Literature Survey, and References. Thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research. Are you planning to publish your next innovative research in IEEE transactions on VLSI 2025? Welcome to Nxfee Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At Nxfee, we provide novelty-based VLSI projects carefully aligned with IEEE transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.